All right, good morning. So, last time we looked at a problem that involved a couple concepts put together. Remember this one, number 101 from Chapter 6. And you had a block on an inclined plane. There was friction involved. There was a spring, so Hooke's law was in play here. And that bad boy was in equilibrium. We're going to look at a situation that also involves multiple ideas put together. But this time we're looking at Hooke's law. We are going to look at connected objects. And initially, there won't be friction in the problem, but we're also going to, as a follow-up, incorporate friction. And so here's the problem. Here's our situation initially. We have two objects. One is sitting on a horizontal surface. And this block. And it is connected to another object here. The string is going over a pulley. But the interesting thing here, the twist, is that this block is connected by a spring to this stationary surface. Okay. We're going to sort of just imagine what's happening when these are connected together and then released. The spring will have stretched from a resting length to a new equilibrium length, and so there will be this change in length of the spring. Let's say from there to there, change in length x of the spring. Initially right here we have no friction at between these two surfaces, and we can consider this direction to be the positive x direction for purposes of solving our problems. So with connected objects, you want them both sort of having the same positive direction tendency, the same, moving in the same direction or accelerating in the same direction. So there we go. We will use two different coordinate systems if we have to here for each object. We have a couple masses. The block here on the surface, let's just call this a 6 kilogram mass. And the hanging block, we'll just call this a 3 kilogram block. Okay. So the question is going to be, how far will the spring stretch? I'm sorry. How far will the spring stretch? I was trying to read my notes about this problem. Forgive me for that. If the spring constant is 120 newtons per meter, and at that stretch, the system is once again in equilibrium. This block has shifted to the right a little bit, this block has shifted down a little bit, and we have a new equilibrium position. So what do we have to do in order to look at this? Maybe I should make a note just for myself that the spring stretches, just so the problem is clear. The spring stretches until equilibrium is achieved, or equilibrium is reached once again. Okay, well here's the deal. I have these two connected objects. They will be each in equilibrium. It's possible that the easiest one to look at first will be the hanging block. Let me see what I can do there. I have a situation where a couple of coordinate axes there, and I got to remember though that for this object, down in my diagram will be the positive x direction, and what that tells me is that if I needed it, this would be the positive y direction, but I don't think I'm going to need it. The only forces acting on this guy will be the weight downward and the tension in the string upward. And because we have a state of equilibrium, I know that those two forces must be equal. Force of gravity on the 3 kilogram block, that's its weight. And here we have force of tension acting upward on this 3 kilogram block. So that's about all I can do on a diagram there. There's nothing else happening to it. However, I can do some Newton's second law stuff. I'm actually going to put that on a different sheet of paper. And also on this paper, I want to simply draw the free body diagram of this guy, 6 kilogram block. Get this diagram set up. Okay, and so here to the right is going to be the positive x direction, and this up will be positive y direction. Now there are more forces acting on this guy. There will be tension to the right. The string is pulling this block, or tending to pull this block to the right. Force of tension. And the spring is going to be a restoring force, trying to pull the block back to its prior position. Since I know this object is in equilibrium, those two arrows, I tried to draw them the same length. Maybe I missed the mark a little bit, but force of the spring. I just need to know that those are the same size. Those two forces are the same magnitude. Now that's not all that's happening to this block. There are some other forces. This block has weight pulling it down. Force of gravity on this guy, and also the surface is applying a normal force in the upward direction. Normal force. But those two forces will also cancel out. This object is in equilibrium, and I'm not terribly concerned with those. There is no friction here. In this current situation for this problem that we're solving right now. And so the forces I want to deal with are the force of tension and the spring force the other way. Now I have to look at Newton's second law and write a couple of equations because I know things are balanced out. So I'm going to do the 3 kilogram mass. What I'm looking at is a sum of forces for the 3 kilogram mass, and this is in the x direction. Up and down in this diagram is the x direction. So why don't I just make a note of that? Okay. And so those two forces, the force of gravity is in the positive x direction. The force of tension is in the negative x direction. But what I know about this sum is that it equals 0. Since these two objects are, or since the whole system is in equilibrium. Alright, so all that tells me is the force of gravity and is equal to the force of tension. Alright. Now how about the 6 kilogram mass? For this guy, the sum of forces, again in the x direction, but for this one the x direction now is horizontal. I have tension, which is a positive force, and I have the force of the spring, which is in the negative direction. But I also know that this sum equals 0. It's in equilibrium. So this tells me that the force of tension is equal to the spring force. Now there's some stuff going on here. The weight of this 3 kilogram block is simply mass of the 3 kilogram block times, I'll put a 3 there, times gravity. And that's equal to the force of tension. The spring force here, well, Hooke's law says that spring force is equal to negative kx. And I know the value of k. It was given in the problem. And x shows up there, and it turns out x is the thing I'm looking for. It's the distance that the spring has been stretched. And that equals the force of tension here. However, I can easily just make a substitution. It's not so complicated this time that I have to add equations together. I can simply say, well, since the mass of the 3 kilogram block times acceleration due to gravity is equal to the force of tension, substitute this business here. And I get a brand new equation that looks like this. And I'm solving for x, so this is going to be the opposite of mass 3 times gravity divided by k. And that minus sign is going to mess me up. So it's going to look like it's going in the wrong direction. But not really. We'll come back to that. Now at this point, I can just substitute some values. The mass was 3 kilograms. G is 9.81 meters per second squared. And I'm dividing by K. From the original problem, the spring constant was 120 newtons per meter. Awesome. Oh, I missed a minus sign, didn't I? There's a minus sign there. So I end up with the distance that the spring stretches is 0.245 meters. Now what about that minus sign? So I've answered the question. There's my final answer. But what about that minus sign? Well, look at this. Okay. The issue is the spring force is actually in the negative direction. And the distance that the spring is stretched is in the positive direction. So those two things are happening in opposite directions relative to each other. So if I were to look back at what I did here, I simply called the spring force a positive value when I got to this step, and that ended up leaving my distance that the spring stretches in the negative direction, or with a negative value. It's not important as long as I understand that the spring actually stretches in the positive x direction. That minus sign simply indicates it's the opposite direction of the original spring's force, the force in the spring that wants to restore the original length of that spring. Okay, so there's that problem that incorporated connected objects and Hooke's law. But we're going to have a new challenge here. We're going to look at this a little differently. And for this, we're going to re-sketch our situation, but slightly modified. So I'm going to have this object. I'm still going to have this stationary surface. I'm still going to have an object hanging here. Pulley, okay. But this time, I'm going to have another object here. And another one here. And the issue is the spring now attaches to that middle block. And even though right here it is smooth, no friction, then we will have some friction between these two surfaces. And so right here there is a coefficient of static friction equal to 0.30. Now, if you recall, friction and the coefficient of friction, they do not have any units. It's just a number, it's just a coefficient. Again, we're going to have the positive x direction, and here, for this object, the positive x direction. We're going to keep this object 3 kilograms. This total mass is still going to be 6 kilograms, but we're going to break it up a little bit. This is going to be 3 kilograms here. This is going to be 2 kilograms. And here, 1 kilogram on the top block. Okay. Again, we're going to ask ourselves, well, when the system is released, the spring will stretch and it's going to reach a new equilibrium. But the new question is going to be, oh sorry, not how. The question will be, will the system hold as before in equilibrium, or so will it hold? In other words, when this is pulling down, creating tension here, and this whole stack of blocks wants to move to the right. The spring is stretching, the spring wants to pull back to the left. Friction between these two surfaces will either allow the system to hold together, or the spring will be too strong and pull to the left and sort of slide the 2 kilogram block off of the 3 kilogram block. Let's see what happens. Or will the stack of blocks let's just say fall over. That's another way of looking at this question. Excuse me. So the deal is this. Essentially, we have the spring force pulling to the left acting on this middle block. And there will be friction pulling to the right. And the friction is caused by the pull of this lower part of the system here. So I can redraw what's happening to this middle block. So enlarge it just a little bit. There is this other block on top of it, right here. And I don't want to forget that guy. But if I just label these block 1 and block 2, and that works because it's 1 kilogram and 2 kilograms, I have a spring force pulling this way. Force of a spring. I have a force of friction here at the bottom surface of block 2. Force of static friction. And now there's other stuff going on. I don't really have a true free body diagram going on here. I should do that, so let's get that created here. Okay. What we're going to look at is, we don't really know, if we'll have equilibrium between these two forces, force of static friction and force of the spring. We're going to find out. But there's more going on here. There's weight. Now, how much weight is acting on this guy? Well, there's two ways to look at that. One way to look at this is there's the weight of object 2 pulling down, and there's a downward normal force from block 1 pushing down on block 2. The other way to look at this is I can simply combine the two masses and call that one force the combined weight of blocks 1 and 2 together. Well, there's going to be an upward normal force down here at this surface. And because we don't expect our system here to accelerate up or down, we know that these two forces, this is normal, these two forces will be equal. That's not a problem. We have to look at, though, these two guys, the horizontal forces here, and see what's going to happen. But there is a connection. When we look at spring force, it's just Hooke's law, negative kx. But when we look at friction force is going to be, for static friction, be less than or equal to a certain maximum value. That maximum value comes from the coefficient of static friction multiplied by the normal force. So now we see normal force come into play, and from sum of forces in the y direction here, I've got the normal force minus weight, and that's equal to 0. It's in equilibrium, so normal force equals the weight, but there's another therefore. Normal force is equal to mg. Aha! Well, that lets me put a substitution of this guy here, so I can bring things all together. This was a sum of forces in the y direction. I'm going to need a sum of forces in the x direction. And I don't really know what's going on here, except I can say, well, the force of static friction is in the positive direction, the spring force is in the negative direction, and I'm kind of questioning whether they're equal. Question mark above that equal sign. Alright, well, let's see what happens. So the spring force, is it equal to force of static friction, is it equal to the spring force? We're going to see what's up. This guy, with that substitution I made here, is coefficient of static friction times mass times gravity. And is that going to be equal to the spring force? Now the spring force is negative kx. So now what's going on here? Well, I have the same tension in the string created with this problem that I had in the previous problem. The same source of that tension here and here. So the spring will stretch the same distance, the same, so I use a value I found in the previous problem, and same spring coefficient, spring constant here. So I want to find out if I have an equality here, or equivalency, if you prefer. My coefficient of static friction, the mass, I have to be careful. I have to look at this. I'm actually going to use the combined masses. So this is going to be a combined mass of 3 kilograms. And then G is, once again, 9.81 meters per second squared. Do I have equivalency when I do this? Don't worry about the minus sign. If you want, you can, say, well, the acceleration due to gravity is downward, but it's kind of an important word. Concern with the values. Are the values going to be the same? And K, the spring constant, was 120 units per meter. X was, from the previous problem, 0.245 Yep, 0.245 meters. So, some number crunching. And here, I need my handy dandy calculator. On the right side, I have a spring force of 29.4 newtons. On the left side, I have a friction force. And remember, this is a maximum value. My friction force cannot get any larger than this. It will be less than or equal to that value of 8.83 newtons for the force of static friction. That is the maximum possible value under these conditions with this particular arrangement. So no, I do not have an equivalency. And with that in mind, the answer to the original question is no. The system will not hold as before. Not at all. What's going to happen is there will not be enough friction force here at where these two surfaces touch to maintain equilibrium with the tension pulling on this lower block to the right and the spring pulling on this middle block to the left. They will get pulled apart and the stack will fall over. All right. Thank you for listening. Hope you got some good stuff out of that. If you have questions, let me know.